Okay, before we want to start with the fourth notebook, the fourth part of the tutorial, let me show you a couple of slides which help you to understand theoretical concepts better of RNNs. It's based on a talk which is on YouTube, which is really nice in my opinion, which I recommend. So I will also give you the slides and URL of the talk in Telegram or somehow else, or maybe I put them in the YouTube description of my videos. So in the slide set, let's have a look at the things that might be interesting. So in this slide set is an explanation on how to use natural language processing in PyTorch. Interesting here for our explanation of LSTMs, which we will discuss now, is firstly just a reminder, how does a neural network work in principle. I think this should already be clear. You have inputs, you have a model, the model creates a prediction, and then we have the label, the target, which we use together with the prediction to create the loss. And then with this information we can update the weights and feed this back into the model to improve the model. From a mathematical point of view, you could formalize it like that. You have inputs x, you have your targets y, the predictions are y hat. So usually these kinds of variable names are used in deep learning for the inputs and the targets and the predictions. And the prediction here, it is created by a simple linear operation. So you have some weight matrix, W, which you multiply with the input, and you add some bias term, and this gives you the predictions. And for the loss between the predictions and the targets, here they just use mean squared error, so they use the prediction, the targets minus the predictions, square it and make the mean of this information. And then for the update of the model, we have the given weights, which is the theta n, and then we change them with depending on the learning rate, which is here the nu or gamma. I think it's a gamma symbol, and then the gradient, which is here in this delta, and we apply this onto the given weights to create our new updated weights. Okay. Here another depiction of the layers in the network, but I think this is basic information. Some common loss functions which we can use, and then maybe this is also interesting, but it hopefully also reminder. What is gradient descent? So you have some lost landscape, and by gradient descent you just want to get in the best case to the minimum, so the best solution, by slowly stepwise going into the direction of the gradient, and then hopefully you end up at some global optimum, or at least a local optimum. Okay, and then let's jump. So I recommend to have a look at all the slides because I think they're quite informative. Let's jump to the part with RNNs, which we want to discuss in this unit. Maybe as an introduction, we used so far linear layers for transforming our inputs to outputs. The problem here is that when you have a bigger context of words, then our embedding and our linear layers will get really large, because the linear layer will then have the input of all all the words at once. So if you have a sentence of 20 words and you want to classify the sentence, then you would compute embeddings for each of the words, or use pre-trained embeddings or compute embeddings for each of those 10 or 20 words in the sentence, and then concatenate, because you need all the words to make the prediction, concatenate all those maybe 100 dimensional vectors together into a larger vector, and then use this as input for the linear operation, which is not really scalable if you have a large text. And the other issue is that you have a fixed size of input. So usually you will use a fixed size of input in the network because you don't want to change the network structure on every training example. It's also not possible. So you have a fixed size input, and if the input is smaller or larger than the fixed size which you defined, it will not match. So either you have to pad the input to fill it up to get to the fixed size, or you have to cut off some words in the end if you have a sentence or a document that is larger than this fixed size. So what we want to use here is something like a sequence model, which is these RNNs. They are made for sequences of things. For example, for different time series data, where you have over time a sequence of inputs, or for text like we have, because text is just a sequence of words. So if we look at the first slide, here they have sequences of other types of sequences, weather patterns, or musical notation, which is a sequence of notes. So how can we train a model on such a sequence? So the idea in RNNs, it's basically very simple. You have an input and you have a hidden state. So the input is whatever the first word. You do some linear operation on this first word, which goes into the hidden state. But the hidden state not only takes as input the current word, but also the last hidden state. So the new hidden state always depends on the existing hidden state and the new input, which is then used together to calculate the new hidden state. So in this sense, you can accumulate information into this hidden state. I think it's easier to use this slide to understand this. So the network is basically like this here. So you have some input, you will do some operation on the input, it goes into the hidden state, and also the last hidden state goes in there. So you have a hidden state at here time step minus t minus 1. You can also at every time step produce an output. For example, again by a linear operation on the hidden state, you create some output vector. So if you think, for example, of a part of speech tagger, you could build it in a way that for every word you feed in, you get an output, depending on the word and the words that were before the word in the sequence of words. But on every word you already generate the part of speech tag output. Okay, so for the next, so you do this, then there's the next word, xt, you feed it into this hidden state together with the last hidden state, and compute the new hidden state, and so on. So it's like a sequential process. And in the hidden state, you try to accumulate all the information from the sentence or whatever kind of sequence you have. Okay, let's switch back here. There are different structures. I don't know where to put. Let's make it smaller, the image of myself. Okay. So which types of RNNs are there? Well, this first one-to-one, it's no RNN because here we don't have like sequential information. Then there is a type of RNN, or it could be built in a way to have one input and then multiple hidden states or multiple iterations in the hidden states to create outputs. For example, if you do image captioning, you give an image as input to the network, and it should create a number of tags of captions for the input image. Then there could be many to one, like in sentiment classification, where you just want to have one sentiment result for your sentence. You only generate an output based on the last hidden state, which should include all the information which is necessary, and then you compute the sentiment information, but you don't use or don't create an output before. Then one common thing is the encoder-decoder architecture, where you first you go through all the inputs until you get to a hidden state at the end of your sentence, when all the sentences get into the network. And then you have this sentence encoded in this one hidden state, and then you could have a second network, or the same network, usually a second network, to decode this hidden state into some other sequence. So when you translate from Russian to English or so, you don't want to create an output on every word, because you need all the information of the sentence before you start creating the Russian translation of the English sentence. So you encode it into a hidden state, and then you have another decoder which then takes this input and creates a sequence from the encoded sentence. Okay. One thing we want to quickly discuss with RNNs is the vanishing gradient problem, which maybe is very intuitive, because when you have a long sentence and you encode the whole sentence in one hidden state, it will be probably quite difficult to have all the information of the sentence in just one vector, and based on this vector to create a long translation in another language. And this problem that the RNNs quickly forget the old information, it's called vanishing gradient problem. And it stems basically from the structure of the network, that when you propagate updates through the network, they get weaker and weaker once you get to earlier parts of the network. Or let's say this way, the words that came in 10 words ago, by all those transformations, you would probably lose the information on those words which were long ago when you encode some sequence. So there's the vanishing gradient problem, or the exploding gradient problem, which is a similar thing when you do compute gradients, and they get bigger and bigger and bigger when you do the back propagation through the network, because if you always multiply values, and if it's values larger than 1, then it explodes. If it's values smaller than 1, then it goes to 0. Okay, this was just a remark on why we use LSTMs nowadays, or GRUs, which are simplified versions of LSTMs, to not forget information so quickly. Exploding gradient problem, we have seen that. Okay, so what RNN cells are there? So the simplest one is just a simple RNN, which we discussed. There are no gates, which they're called, and we have those problems of vanishing gradients. They forget really quickly the information that you gave. To make this RNNs better, there are two other types of cells, LSTM and GRU. Now we will not discuss exactly how they work. It is on the slides, so if you're interested, just have a look on the slides. It's a bit more technical. They have different parts in the cell to where the system learns when to forget information, when to update information in the cell, and so on. So it's better at remembering old information. For example, you would want to forget information if you have multiple sentences, and maybe if one sentence ends and a new one starts, then probably you want to forget more information than you would usually forget, so you focus more or you keep more of the new information. Just as an example. Okay, so here is then some mathematical formula for like explanations of LSTMs, of GRUs, and how to use them. Okay, with this, let's switch back to the tutorial from PyTorch.